Now I'm going to talk about quantum variational methods. They are very useful techniques to study both quantum chemistry and material design. And they have lots of applications provided you understand the what you call the logic behind it. And there is nothing specific in terms of putting in a quantum computer. The techniques are completely okay if you run it on a classical computer as well. The only thing is on a quantum computer, you will be able to do something little faster, more efficiently. Noise is going to make a disturbance. All right, I don't know what to do about it. So, let it be. I don't know what they can do about it. Can they do this banging and all that stuff outside somewhere so I don't get too much noise inside?
On the floor, sir. These chairs are being fixed on the floor. So these are not moving chairs, that's the issue.
Okay. Yes, okay. Yeah. So, what do these variational methods focus on? And they are most useful for studying the properties of low-lying states. Okay, so what you need is a Hamiltonian bounded from below. So the minimum energy doesn't go to minus infinity. Okay, there is a ground state somewhere. And then what you study is properties of ground state, then excitations on top of the ground state, some features which are related with these excitations are transport properties which describes dynamics of certain degrees of freedom, and in general it's all part of the low-lying spectrum of the theory. Okay. So this is an area of applications, and we kind of encounter lots of systems of this type because we know that the systems all relax on their own to the lowest lying states. There are some fluctuations and you want to study them and figure out where they will be useful or what kind of dynamics is present, etc., etc. So this is what you can call the background you have to keep in mind that we are going to look at this kind of features. Now the principle which is involved is very simple, and that just comes down to using the properties of Hamiltonian in a particular context. So one can write a generic Hamiltonian in terms of its eigenstates. The Hermitian nature of the Hamiltonian guarantees that these are all orthogonal. And I can then write any generic wave function also expanding in the same basis. Then the property which follows immediately, without knowing any details about what these states are or what are the expansion coefficients are, is what is the expectation value of H. Okay, so this is nothing but, well, I will write it down. Explicitly, you plug in all the properties by putting in Ci for the wave function coefficients, and then H acting on I just produces the energy values, and the states are orthogonal, so it's easy to express the expectation value is nothing but just this. Now I can write the specific form which separates the ground state. So this can be written as term which has the ground state contribution denoted by 0 and everything else which are positive indices, and the contribution which is separated, EI had a coefficient actually C0 square, but all these things also holds at normalization. So I can take out all the Ci square and put it over here, and then I can write it as a difference, and the trivial result which appears at the ground state, this is all higher states, so Ei minus E0 is always positive, and you have a strict inequality. And this is the so-called variational principle of quantum mechanics, that you just make a guess for some wave function and calculate the expectation value of the Hamiltonian. You will get an answer which is always bigger than the ground state energy. Then you can have some parameters which are essentially this coefficient Ci, and you vary the parameters to minimize the bound. Yeah, so this is what you will find in most quantum mechanics textbook. But one can go a little further and calculate not just the expectation value, but also the variance. Okay. So what is variance, which is written in different ways. You can write it either as this, which is mathematically equivalent to this. And now you do the same substitution. So what you will get is a same coefficient E I minus, this is the constant. And now I can do the same separation, which will give the first term is just this, and then I will write the remainder with this is subtracted, the ground state is. And where does it go? It's a square was outside. So I can rewrite this as again an inequality provided the second term is positive. And I know already that h is bigger than E0, so it's better to write this as h minus E0 square. Then the quantity under the square is positive, and provided this quantity is positive. And what does it mean when it will be positive? It will be positive when h is closer to E0 than to h is closer to the ground state and than to any other eigenstate, then this number will be positive. When this will be true, which means that you should have a good enough approximation to the ground state, then this structure will be useful. And what will it give you? I mean, it's well, kind of ensured. Just a spectral gap. If you are closer to the ground state, then everything else will be in place. You don't have to have such a what you call strong constraint, but it's a sufficient condition. Okay. So what is the use of this identity? That now I can write together with this a double-sided bound. And this is a bound which you will not find in standard textbooks, but it gives a lower bound. I'm just rewriting this equation, making use of this inequality, and I know where h and e0 are there. The square root is taken, but I know h is bigger than e0, so that is a positive sign. So this is very useful because now you have both upper bound and lower bound, and you can judge your accuracy much better than just having a one-sided bound. You will not find this in the standard quantum mechanics textbook for the very simple reason that most of the applications in atomic and molecular system, the Hamiltonian has a Coulomb potential. And Coulomb potential had term which is 1 over r in the Hamiltonian. Square it, it becomes 1 over r square, which is even more divergent, and the integrals are not necessarily convergent when you calculate it. So in practice, people in chemistry don't use this because it's there, but the integral is divergent. That means this bound will be way off and not of any practical limitation. So this is not for Coulomb interaction, but we will be ending up using it for spin models. Some qubits interacting with some neighbors, and there taking powers is no problem at all. Okay, Hamiltonian just have a, say, nearest neighbor interaction. All you will get by taking a square is 2 steps, so next to next nearest neighbor interaction. That's all. I mean, nearest neighbor, next to nearest neighbor, you continue more higher powers of Hamiltonian will just give you one more next step in the interaction, nothing worse than that. And so many of these variational algorithms which are being developed to run on the small models of quantum systems, they can be evaluated or estimated in accuracy using this kind of bounds. It is something which people have not used very much just because they've forgotten about this kind of bounds. It's an old story. You'll find this kind of derivation from the beginning days of quantum mechanics, but then when it's not used for many years, people forget about it. And one can do better, that still higher moments of the Hamiltonian. This is only the first and the second moment. You can calculate if you calculate, say, a third order or a fourth order expectation value, or rather the what is known as the cumulant, because you always subtract off the mean contribution, you are only worried about the deviation from the mean. And it's an open problem, rather people have not studied it at all. You can develop better approximations using the higher order moments. There are some claims which probably can be made more accurate in a systematic manner. It's just a open problem as far as I know. So yeah, this is something which will appear on and off in this course. There are some things which are known and something which are not known. It's up to somebody to figure out whether you can make a progress in that direction or not. Yeah, this kind of bounds. Can you get a more complicated expression which is closer to E0 in some sense? Now this is the story, but there is one important feature which is buried in this, and that is useful from the point of view of accuracy, which again you will not find quoted very much in physics books, but for numerical results it's extremely worthwhile to keep in mind. So what is the feature that psi that the expansion here depends on some coefficient Ci, but the expectation value only involves Ci square. So when psi has accuracy of the estimate of energy is much higher. What does it mean? That if you get the wave function right to say 10%, the energy will be correct to 1%. And that is quite a dramatic change. And it's very useful that you can get tight bounds on energy without working very hard on what the wave function is. And you can work out one of the simplest examples in quantum mechanics, that say look at the hydrogen atom. You know the wave function is exponential e raised to minus r divided by the Bohr radius. But suppose I don't know how to solve the Schrodinger equation and get that result, I'll just put another wave function from a completely different model which I know how to solve very well, which is harmonic oscillator. So I just write a wave function as e raised to minus alpha r square, the Gaussian. and just calculate the energy and minimize the whole thing as a function of alpha, you will be surprised how accurately you will produce the ground state energy. It doesn't matter very much how accurate your wave function is. The ground state energy turns out to be quite good. And that is something worth keeping in mind. And this result actually has a generalization which you can easily prove. It's basically a theorem that if in some perturbation expansion, so suppose I make an estimate and I have some parameter which I'm expanding, and I know that this thing is good enough to some order k, and the errors are of the one higher order. And then this term is square of that. This is some Taylor series expansion. If you have some means to calculate it, many times such things are done in perturbation theory where you have a Hamiltonian plus some perturbation and you expand in the powers of perturbation. The original wave function you can calculate term by term in the perturbation series up to some order. And then if you want to calculate the energy, the number of the exponent basically doubles. And this result is just a particular case where k equal to 0. It's nothing more than that, but this is something which you can keep in mind. It is worth knowing that it's not just a hand-waving argument, it is rigorous. What else? Oh, yeah, so now the job is to find a good starting point. So and this will be a major exercise for any particular system that you want to study. You want a good starting point, and then the convergence is going to be quite impressive. And this requires knowledge of whatever it is that you want to study. And what happens for quantum theory is that finding this wave function of a many-body system, you have to develop some intuition about correlations between different parts. If you are able to build that inside the wave function, you will be able to do a good job. And I will give explicit example, but something else I can add at this particular point is that one can take advantage of various symmetries which exist in the problem. So many symmetries appear in the problem, and to give an example, just consider the ordinary harmonic oscillator. The potential is symmetric under x going to minus x. Then what will happen is I can separate this possible wave function into two parts, functions which are odd and the functions which are even. And that symmetry will survive in all the analysis because of this orthogonality property of the Hamiltonian, that if you are in a even sector, then you will do the analysis and find the properties of the states in the even sector. It will never get any contribution from the odd sector, and if you look at the odd sector, you will again find all the properties in the odd sector. And though the sectors don't mix, that means that you are going to find the ground state in each sector separately. They may not be the overall ground state, but on each sector you can find the ground state, and then you will see patterns that one of them is overall total system ground state, the other one is a different symmetry sector, it is an excited state, etc., etc. So low lines and this is a feature which is very important in studying various kind of excitations, because excitation typically will change the symmetry from one description to another, and then you can find the lowest state which contains that particular excitation, and then its corresponding properties. So this is something which can be kept in mind. And since I mentioned harmonic oscillator, it has a ground state which is actually symmetric, but the potential doesn't have to be only quadratic. I can take a pendulum where the potential will look like cosine x. The same separation between even and odd sector will survive for the pendulum, because what is needed is only the symmetry of the potential and not a particular form, like it's a quadratic form or not. And the symmetries which appear in bigger problems of chemistry, there are all kind of rotational symmetry. For example, in a hydrogen atom, the potential is isotropic, and you have all the different sectors which can come out from there, and you can study S wave separately, you can study P wave separately, even when you put in extra perturbations which are not just the Coulomb potential. So those things all go along with this kind of a description. But one thing which is again a kind of theorem, that the total ground state has the same symmetry property as that of the Hamiltonian, and this is qualified with a particular caveat which is going to remain true in our case. Systems are finite dimensional. The number of degrees of freedom goes to infinity. You have to worry about other stuff, but we are not going to go that far. So for example, for a pendulum, you know that the ground state, whatever it is, it's going to be symmetric. It may not be a Gaussian, like a case of a harmonic oscillator, might be some different function, but whatever it is still symmetric. So those are the kind of features which remain, and that is a powerful analysis, which again can be formalized in terms of theorems and things like that. It's useful to know that such things are present on a rigorous framework. Yeah.
When we separate sections, does that mean we are separating odd wave function and even wave functions?
You can choose that. I suppose I want to look at a harmonic oscillator, but psi, which is always even, which means the psi of minus x equal to psi of x, doesn't have to be some particular form like a Gaussian. Any other stuff you can put in, and it will give you a lowest spectrum among all the even sector states. But if you say that I am going to choose my initial guess, this is just some ansatz, whatever it is, which you have to pick, and the coefficients Ci are adjustable. So if I say I'm going to take all the functions where psi of x is equal to minus psi of minus x, then I will look at all the states, what are the available quantum numbers which may appear in the solution, and I will find the lowest value inside that. So for example, if I do it for a harmonic oscillator and the quantum number is n, then one sector will have n equal to 0, 2, 4, 6, 8, etc. The other sector will have n equal to 1, 3, 5, etc. And I will get the behavior inside those particular sectors. They separate out. So this is what quantum mechanics tells us. Now, where it is useful, and that is also worth knowing, though it requires some knowledge of basically chemistry in a certain sense. And so here are some numbers that you are studying features of energy and then dynamics on top of that. What are the numbers? Because ultimately you are making an approximation and you have to see that how far of this epsilon I need to evaluate in practice. Okay. So, well, there are all kind of things in chemistry, some things which are ionization of the atoms, and I will just write down the numbers. This is known as benchmarking in some sense. That for hydrogen, we know that the energy is 13.6 electron volt. And in general, this ionization energy are in UV and X-ray spectrum. This is in general. In chemical reactions, you actually don't go this far. Okay, you don't ionize any of the atoms. What you are interested in is formation of bonds and various transitions, not completely knocking out the system. So what are the energy for transitions? These are electronic transitions. And what we know that they are all connected to visible light. And the range is this, and 2 to 4 electron volts, and spectrum is sometimes written in terms of wavelength. It is 300 to 700 nanometers. Now, why this is visible light is not an accident, because it's the other way around. Our eyes have developed to look at these transitions. Eye is a detector, and of course light falls on it and you want to see some changes, so some atom has to get excited from one level to another. That will produce some chemical reaction, and then our brain says, yeah, something has happened. So we see it because precisely we are looking at these transitions and making use of it. So that is why this all stuff is in visible light. And from the practice of looking at all kind of chemical reactions, this is the most important region, because all the transitions are taking place there. It's a generic scale, but it is the important scale, and which means that if you want to understand these processes, then all these energies you have to determine up to this accuracy in some sense. Okay, that is the overall scale. Can emission, absorption, whatever it is, there are transition between specific energy levels. There are discrete energy levels. Quantum mechanics tells us that much. Okay. So you can, well, I can give more values. That there are chemical bonds which you can study, and here there are various types. There are covalent bonds, and the range of that is about 2 to 5 electron volts. Then there are ionic bonds, which will be probably little bit higher, but not too much. They are in the same range. But what is much smaller is something which is known as a solvation energy. The ions are you want to break up the molecule like sodium chloride, it will require a lot of energy. But you want to put it in water, it will dissolve. And there is solvation energy, and that does not require too much effort because it's a rearrangement. It's not really breaking it up in the sense that the water will take care of the positive and the negative ions. And some say that that scale is much smaller, and the similar scale is also the value for hydrogen bond. It's about 10th of an electron volt. And there are things which are much smaller than that. The vibrational energy levels, which are basically bonds, are not static. The nuclei move with some amount of energy, and they have a scale which is not the visible one, but it falls in the infrared. And then there are rotational levels which are much smaller than this. And they fall in the range of microwaves. So when you heat up your food in the microwave oven, you are not breaking any bonds, you are just changing the rotational energy levels, and that is enough to put in certain amount of energy and warm up the food. So this is just a list, but what gives us the overall picture of how accurate the answer should be, and that is characterized by the thermal energy scale, because all the reactions which we look at in chemistry, they are taking place in our real world. You might stir something in a solution, or you might study some material, but most of it is all room temperature. And that scale is KT, and room temperature is say 300 degrees Kelvin. This is the Boltzmann constant, usually appears with the temperature. And what is this value? And this turns out to be about 1/40 electron volts. So the fluctuations which are present in the system are at this particular level. And that means this is the scale, for example, what is the kinetic energy of a molecule. Okay. It's of the order of KT. That's what the ideal gas theory will tell you, whatever it is. And this is the number, those kind of fluctuations are present. And then looking at all the numbers, it's good enough that how accurately you should measure. Well, you are looking at energies up to some level of this visible spectrum or these bonds, and the fluctuations are of that particular size. So there is a something which is called a chemical accuracy, how accurately you want to determine something. It's only like 1 part in 100. And for a molecule, not too big, I'll just assume order 10 atoms or something like that, then there are many bonds and they have to add up all the uncertainties, or maybe another factor of 10 I will lose. So that gives us a good criterion for what is this epsilon that I should aim for. And so lots of quantum chemistry calculations, they are very happy if they get 1 part in 1,000 accuracy. That's all there is required, and if your variational approximation gets you that far, it's very good. And so that is now the job for the computer. Okay, you are not looking at other kind of evaluation problems where you needed an answer to whatever 32-bit, 64-bit, whatever it is. You are looking only for a limited accuracy, and even if you have noisy systems, as is the case in terms of quantum computers being developed right now, maybe you can get something out of it. And that is a important criterion, that this is something which is achievable without going into all kind of complicated error correction protocols and things like that. Maybe you can do something with the available system, get some useful results out of it. So that is a practical lesson from all these exercises, whatever. Okay. So, fine. Now, let me give some examples explicitly. Of where this kind of numbers will appear. Okay. And or where the conventional methods don't work very well. So these are quantum systems with non-local correlations. If everything was completely local, we would have solved one atom problem and be done with it. Nothing more complicated will happen. But then you can have many situations where the correlations are extended and where quantum dynamics will show up in the solutions in indirect fashions, and that is the places where you do not have a good understanding of what the wave function would be. You can have ansatz, but the kind of features which we studied in analyzing quantum information are going to show up in these kind of examples, and I will just give some names. So there is one label which is used is called frustration. That means you can't do a local minimization of individual degrees of freedom. You have to have a global picture. And that is where the non-locality will become important. So the simplest example is three-spin system, which is antiferromagnetic. Okay. So there is no way to satisfy all the constraints simultaneously, because if I say this is up, I want to make this one down to make it antiferromagnetic, the third person cannot decide. So there is no local feature which will fix the configuration. You have to look at the whole thing. And this kind of scenario can now become part of a bigger system. You can have a lattice of these triangles, and you can ask what is the ground state of the system when the interaction is antiferromagnetic. There is no good local description. And that is labeled as a frustration because you can't satisfy all the constraints locally. You have to find a global correlation which will give you the overall scenario, or what happens actually more accurately is there are many candidates. And the final wave function may be even a superposition of all these many candidates. You just can't tell which one it is. So there is another label for this kind of scenario, which is called a spin class. Quantum liquids. These are all related things, and if you find a global minimum, the system will behave more like a solid. You went into that ground state and everything got nicely fixed, etc. But when you can't satisfy it, things will keep on moving. That's why they are liquid. Glass is a form of a liquid. It's highly metastable, but it is still a liquid. It can't find its ground state properly. Or rather, it keeps on shuffling around many possibilities, and these kind of systems are there. And if you want to study it, you have to look at non-local correlation. Okay. The next label is something called tunneling, which again, we know there are multiple ground state, and you keep on going back and forth between them, and the overall thing is superposition. Okay, the typical scenario is a kind of double well potential. So this And we know that there are many examples of tunneling systems in quantum chemistry. They are actually reasonably common, and one of the most illustrative of that is this hydrogen bond. It is literally a tunneling in a double well potential. A hydrogen is either on one side or it is on the other side, and it keeps on moving back and forth. And if you want to understand where the energy comes from, it comes from this tunneling effect. And if you don't have tunneling, hydrogen bond will not exist. There is no classical explanation for it. So this is an exclusively quantum effect, and it's non-local in the sense that you are looking at multiple possibilities. It is not just one.
Sir, in hydrogen bond, which particle tunnels?
Hydrogen bond is actually a proton tunneling, say, between two oxygen atoms in water. When you write water formula is H2O, but you look at the liquid, the hydrogen is not bound to a specific oxygen at all. It keeps on jumping back and forth between different oxygen atoms which are there in the liquid. And that tunneling effect gives a specific contribution to the energy.
In normal H2 bond also this thing happens. In normal H2 bond.
Normal bonds, okay, I will come to that as well. I can describe what happens in a particular chemical bond. Before that, there is another name which is used in chemical literature more than anything else. It's called resonance, which is again multiple configurations which are superposed. So that's how we write it in the quantum language, but if you look at the chemistry textbooks, there are things like this, they call it resonances, not superposition. But one of the well-known example is this molecule of benzene, which can be written in alternating single and double bonds in two different manners. What is the actual wave function? It is neither this or that. It's a superposition of the two. And the chemists like to use this language. It's called resonance. We don't mean that is where you land up if you are trying to look in a chemistry textbook for interesting systems. For a physics description, it is just superposition. Okay. But that is where the quantum effects will come in. So you have to find out there are multiple configurations. You superpose them. What happens to the energy? Okay. And these features are going to appear in the analysis of chemical bonds, which I will now explain in the quantum information language. What happens inside? They are all buried in different manner, but you can look at it in a separate language as well. So look at a textbook. You will find that there is one atom, it has some orbital, there's another atom, there's another orbital, and they come close together, these orbitals will overlap and it make a bond. Okay. That's a completely classical description. But then you can ask, what is the structure in actual space of this particular bond or the orbital, what happens in terms of its wave function description. And you will find very easily that this orbital overlap gives double-peaked wave functions. It's quite generic. And you can understand it in a rather crude manner that suppose you have one atom here and it has some orbital, another atom which has some orbital, and you bring them together, and what you will get is some kind of structure where this come next to each other, some overlap is there, and that gives something in the middle, but the large part of the wave function is still around the atom's own nucleus. This is what I mean by a double-peaked wave function. So if you literally are able to solve even a simple molecule like hydrogen gas, H2, to find the wave function, it will look like that. It's not that the maximum is in the center of the bond. No, it doesn't happen. And the reason for why the little bit of separation remains is because the two electrons, they have Coulomb repulsion. So the base overlap is not on top of each other, a little bit separate. Okay. And this is a generic thing, or the other possibility from the point of view of the symmetry sector, which I described, is this: they overlap but with opposite sign. So in some sense, you can call this a two-dimensional Hilbert space. I introduce an interaction, which is a off-diagonal element in the 2 by 2 matrix, and find the eigenstate. One of them will be symmetric, the other will be antisymmetric, and they will have this kind of wave functions. You have to be two solutions every time this thing happens. So even in this particular case, when I say it's a superposition of two, one will be symmetric, but there is an antisymmetric part also. And they are different eigenstates, they have different energy. And many times the excitations which take you from this to this and vice versa, they play some role in chemical reactions. And then you have to, worry about how to include them properly in your model or whatever theory you want to put together. So there are names, I think the chemists use a label. This is, I call it a symmetric and antisymmetric. But the chemical literature has a German name for it, which they will just use a subscript. One of them is Gerard, and the other one is called Ungerard. So they will have labels with a G and U. Those are the two states. But that is what we can figure out without doing detailed analysis. This thing is always going to be there.
These two organic states correspond to the splitting of the energy.
Yeah. So many times it gives up energy states which are not too much far in separation. And what is known as the spectral gap is often the transition between these two. And the spectral gap has many importance in many chemical process, how quickly the reactions occur and what are the rates and all those kind of things, transition amplitudes. But both these things were happen. And you can look at it in a little bit of a different way also. You can call it tunneling. The tunneling produces again whatever the hydrogen bond, this kind of wave function. A proton is closer to one oxygen atom or the other oxygen atom, and if this thing exists, it may not even exist as a bound state. In case of hydrogen bond, it breaks up. It goes into the continuum. And the two atoms basically just move apart. But those kind of features are also, it's connected to tunneling in some particular fashion. But look at it in another way to use full connection for, again, the quantum information language, that this is what you see when you are sitting in the so-called rest frame of the nucleus. Okay. But now I can say that no, I am going to sit in the rest frame of the electron. Okay. I'll just imagine that it's a point of view. And then from that point of view, it connects to the feature which we have seen in quantum theory called entanglement. How so? Suppose I sit in a rest frame of the electron, then I will find two possibilities. One nucleus is closer and the other is farther away, or this one is farther away and that one is closer. Okay. So if I use the 0 and 1 labels, it brings a state 0, 1 plus 1, 0. And that we know as a well-known entangled state, Bell pair, whatever you want to call it. So these have all these features buried inside it. So in so these features I am just describing because they are all there. I mean, chemistry textbooks will tell you a lot about chemical bonds, etc. But we want to extract what is the important quantum part inside it. And those features which we have used in quantum information and algorithms, they are appearing here in a different point of view. And that is the place all the non-local correlations or stuff which we want to put in our investigation methods, they will become useful. Because we have methods to deal with it, and these are the questions where those quantum correlations are important. Without that, you'll not be able to study the system fully. And now you want to develop quantum algorithms which have these features included from the beginning. Okay. So,
This seems like a local code.
hmm?
This seems like a local code.
It's local, but between two objects. Local will just mean only one atom for the time being. So these are correlations between two atoms. And well, you can have bigger molecules, and then these features will spread over a larger set also. But the point is that you have to understand these quantum correlations if you want to understand these materials properly. And the usual chemistry description is limited in this particular sense, and that is where doing whatever quantum simulations can do a little better job. Okay. Okay, so there's one more thing I can bring in. Which goes more on the computational side, but it has important connection in physics, quantum physics specifically. And that is a situation arising from genuine quantum properties which are identical particle symmetries. There is no classical analog of it. Okay. And by this I mean there are two types of particles in nature, bosons and fermions. The boson wave function is always fully symmetric, and the fermion wave function is always fully antisymmetric. And you want to study all those phenomena, you have to keep that in mind. There is nothing you can do in terms of any shortcut. So, how do you include this symmetry? The only answer you have is a superposition. You write a wave function, then add all the terms which are allowed by exchange, various labels. So, if you do that for n particles, count all possible arrangements, there are n factorial terms. And that's a huge thing in terms of complexity. Okay. There is no shortcut to the particular wave function, and in case of bosons or fermions, there will be n factorial terms. So, you have to include that exactly. You cannot skip, and well, here I can write down a structure which is known as a permanent. I have to invent a notation, but let me just use a matrix. So this is just a arrangement. What it stands for is the first particle has wave function psi1 going up to the nth particle has wave function psi n, and we arrange all these combinations. In one direction you vary the label for the particle, in other direction you vary the label for the wave function, and you can now ask how many terms can be constructed from doing all the jugglery. This is a description for or rather a notation for the n term, and just let me put a symbol P for permanent. That is what it is. And now the question comes, if I want to make a model, I have to include all these terms psi and then calculate the expectation value. But the jump from n to n factorial is complexity wise extremely non-trivial. And there is a rigorous results. So evaluation of this permanent belongs to the complexity class, which is labeled by this symbol. It is hash polynomial, and this result was explicitly proved by Valiant. What does this hash p stands for? So hash p counts it is a counting problem. If you some description, hash p will tell you how many solutions exist to that particular answer compared to a simpler scenario, which is the NP, non-deterministic polynomial class, which asks the question, is there a solution? So this is not satisfied with is there a solution, it has to how many solutions are there. So obviously it is much harder. And well, what Valiant proved actually is that this is not only hash p, it is hash p complete. That means if you solve it, you will solve all other problems in that particular class. And so this is a what you call out of reach problem for any computer or even any analytic method, whatever it is. It's just too hard where the number of degrees of freedom, this n becomes large. Nobody has any clue, and the practical situation is that there is a well-known problem studying the properties of liquid helium. This is helium 4. nobody has a good answer. Even after all these years of quantum theory, etc., what is the ground state of the liquid helium? Can you write a good description for it? What are its excitations? Out of control. No method exists which is numerically so. There is only one description you will find. And that is Feynman tried to calculate the properties of liquid helium by using these n factorial terms in the symmetry explicitly, and even after all these years, nobody has done anything better. So you have a description about the ground state, excitations, but it is all approximate up to a certain level. And even though this is a very interesting material, superfluid on top of everything else, you want to understand its properties, well, there is only a limited knowledge available. Nobody has found a better solution. And in contrast, there are fermions. It's a fully antisymmetric wave function that is completely okay, but this n factorial terms they can be arranged in the same structure, but not a permanent as a determinant. The only difference between permanent and determinant are the relative signs. Here the signs will alternate. Here all the signs are the same. And why they alternate? Because you can say that I will interchange this 2 row, which is for a determinant will flip the sign, and for the particle it will flip the label. Now, interesting difference between a permanent and a determinant is that determinant can be evaluated by an effort which is only order n cubed. Even though there are n factorial terms sitting in the full expansion, we can take this matrix, do a Gaussian elimination, subtracting one row from the other, which doesn't change the value of the determinant. You will convert it into a triangular matrix, and for the triangular matrix, the value is just the product of the diagonal elements. So the determinant is very easy to evaluate for case of fermions, not for the case of bosons. And all the quantum chemistry problems fortunately have fermions. Whether you are studying electron structure, they are all electron fermions, or even if you are studying something like a hydrogen bond, it's a proton, it's still a fermion. So these methods to study all those things are actually something which is practical even when the number of particles start growing. It grows as a polynomial, not as a factorial. And so all we are going to look at from the next lecture onwards is quantum algorithmic methods for multi-fermion systems. And well, we'll see what are the kind of things we can construct, but there is a major difference between bosons and fermions that you should keep in mind. I mean, you can still ask some new model or some new material which is made up of a bunch of integer spins instead of a half integer spins. How it will behave? Well, there will be a lot of open questions because those are bosonic particles. And many answers in those cases are not known. But for chemical processes, fermions simplify the job quite a lot. You still have to worry about this n cube. Some effort is needed, and a lot of these methods will be focused on how you bring down that power as much as you can.